we got into alcohols mainly last time. And again, a reminder that alcohols have a functional group of OH. So when we do see that sort of OH on there, that is the functional group of an alcohol. It's an important sort of group as well, because as I might have mentioned last time, it also is a polar sort of group that's on that molecule. And that means that there's more partially negative on the oxygen side, more partially positive there on the hydrogen side. And it gives certain alcohols, especially these kind of smaller alcohols, the ability to be sort of soluble in something like water, because they can interact with water through hydrogen bonding. And a reminder, hydrogen bonding is a bond between a hydrogen that's attached to a nitrogen, oxygen, or hydrogen. I'm sorry, nitrogen, oxygen, or fluorine. And in this case, it'd be like the oxygen of one to the hydrogen of the other. Now, as we would talk about, solubility does decrease as you sort of build up the number of carbons that are on there, because in most alcohols, the rest of the deal is pretty much just chains of carbons and hydrogens there. And at some point, if you build out sort of the carbons and hydrogens to usually around 6-ish or so, or a little bit more than 6, you really do start to see a big decrease in the solubility of an alcohol in water, because it's just too big. And sometimes it's referred to as steric hindrance, which just is a fancy way of saying the non-polar part's so big, it kind of gets in the way of water being able to interact with that OH group that's there, so they really can't sort of interact well with one another. But usually up to about 6-ish or less carbons, you have some good solubility in water because of that OH group. Also, there are some alcohols that have multiple OH groups. So if you actually have something that has multiple OH groups on it, that's also going to increase the solubility of it. Again, it gives it different places where water could really interact with it. When we go to name alcohols, the thing that really does get the priority is the OH group, and starting around 3 or so carbons, you have a couple of different places, or a few different places where the OH group could be located. So we do have to give the number of where that OH group is at when we get to 3 or more. So if we had something like this. Again, we would go with our longest carbon chain here, and that is 4 carbons, and that is based off of butane. Because it has that OH group, that then will make this butanol, OL, like alcohol. And because that OH group is sort of important, we do need to give the location of it. Again, in this situation, it could be at a couple of different carbons within this molecule. So because the OH group gets the priority, when we go to number the chain, we do want to number whichever way will give that group, or the OH group, the smaller number. So in this particular case, going right to left will achieve that. That puts our OH group at carbon number 2. If you went left to right, that would put your OH group at carbon number 3, which obviously is a larger number. So this would be something like 2-butanol. Questions on that there? Obviously, as well, once you determine sort of which way you need a number for the OH group, you got to stick with that numbering for anything else that may be attached. So, if I just kind of threw a chlorine in here, for example, that then would have to be at carbon number 3 in that example because of the way we numbered it for the OH. So that would turn it into like 3-chloral 2-butanol would be the name in that case. Yeah. 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 There's not. I was just explaining that as you build out this sort of chain of carbons, I didn't finish it out, but I guess I should have drew a line there. But as you just continue, is kind of that theme of carbons and hydrogens, it builds out really the non-polar part much larger, and it kind of gets in the way. Yeah. So if I was to stop there, I should light up on hydrogen. You're right on the end there. Yep. Other questions? Okay, so we talked about naming, and then again, obviously all the groups, and also, you know, if you have more of a cyclic sort of alcohol, you know, it's basically works the same way. You know, here, this guy, the major thing here would be based off of cyclohexane. Again, we see the OH there that tells us an alcohol, so that becomes cyclohexanol. Again, if there's nothing else attached there, you don't need to give the number for the OH group because it's assumed to always be carbon number 1 wherever it's at. And even though I drew it there on the top right, I could have drew it on any of the carbons there, and it'd basically be the same thing. It's just the molecule kind of turned around. But if you did have, you know, something attached, again, I'll just kind of throw a chlorine in there. You would then obviously need to number the other guy that's attached there. Again, you wouldn't need to give the number for the OH because, again, wherever that is would be 1. In this case, going clockwise would actually get us the smaller number if we went clockwise versus counterclockwise, which would give us a larger number. And again, that would turn that into something like 3-chloral cyclohexanol would be the name of that guy there, like 3-chloral cyclohexanol. This is not to be confused, sort of the cyclohexanol with also something that we talked about, which is sort of in the alcohol group, which is one that has really the base of it is a benzene ring, which is this guy, and that has an OH on it, and that is phenol, and that's just sort of the special name. So there is a difference again between this ring structure that has basically no double bonds, right? And that's again just basically cyclohexane versus this guy here that has 3 double bonds, and that is what is known as benzene. So that's sort of the difference. Sometimes people look at like these two and go, aren't they kind of the same? But again, those double bonds in the middle do make a difference in terms of the name of it. And again, that's sort of a historical name that's hung around a long time. So people still sort of use that. And again, even if you have something else attached there, again, I'll just throw the chlorine in. If you had something else attached there, you would still use the phenol as sort of the base of the name. And again, where that OH would be carbon 1, and then you could go clockwise there to get to 2. And again, that would turn that into something like 2-chloral phenol in that case. Any questions on that there? We sort of finished up, I think, talking with alcohols again about some of the reactions that they undergo, which was sort of related to the lab I think you guys were doing this week, which is basically they undergo really redox reactions. But more specifically, they do both actually, but they do oxidation reactions. And there's several definitions of oxidation, but sort of the one and reduction that we sort of focus more on in organic chemistry versus sort of inorganic chemistry. In inorganic chemistry, when we're talking about sort of reactions, you know, we really focused in on sort of electrons being gained and lost, and that works really well when you got things like metals and stuff like that. In sort of organic, we really do focus in on kind of 2 other definitions for these guys, and oxidation means that it has gained oxygen, again, from going from the reactant side to the product side, or it could mean that it lost hydrogen, same deal, going from the reactant side to the product side. So whatever you're looking at, either gained oxygen or lost hydrogen, would be an oxidation. And a reduction would pretty much be the opposite there. A reduction would be the loss of oxygen from reactants to products, and the gaining of, if I could write, gaining of H2 there from reactants to products. So remember, as we sort of talked about when we were talking about types of reactions, these things really do sort of occur together. So, you know, something gets oxidized, something else does get reduced. So again, that process really does sort of occur together. And in terms of the oxidation of alcohols, it really revolves around whether you have sort of a primary, a secondary, or a tertiary alcohol that is happening. And again, we also talked about last time how you could identify primary, secondary, tertiary. And one common way is always to kind of look at the carbon that has the OH group attached to it. And again, how many carbons are directly attached to it. So in this case, this would be 1, which would be a primary alcohol, a carbon that has the OH group attached, that has 2 carbons attached, would obviously be a secondary alcohol. And lastly here, a carbon that has 3 carbons attached to it. I didn't draw all the other hydrogens in, obviously, so just here, carbons. That would be your tertiary. So kind of very similar to how you can classify carbons as primary, secondary, tertiary. You could also classify alcohols the same way. And again, I personally like counting the carbons. Some people like to count the hydrogens that are there. So kind of the same idea, but I personally go with the carbons myself. Any questions on that classification stuff there? All right, so we did talk about sort of the reactions that occur with it. And if we did have a primary alcohol, such as ethanol here, if you do it this way. So once again, this would be a primary alcohol. If we look at again, the carbon right here, that has the OH group attached, again, directly attached to it is just 1 carbon. And what happens when we do the oxidation here, again, is it's also sometimes symbolized by the little kind of brackets with the O in it. It is the loss of H2 that we are looking for here. And at 100% of the time in this type of reaction, pretty much always occurs the same way. You're going to take an H off of the carbon that's attached to the OH group. So it really doesn't matter which one, but I'll just kind of take this guy. So we're going to take a hydrogen off of that carbon. And then 100% of the time, it is the hydrogen that is part of the OH group that also goes as well. So we're going to take a hydrogen basically off of there. And when we do that, that is basically the oxidation part of it. We get our loss of H2 coming out on the other side from those 2 that are there. Now, as I mentioned before, and as we'll see as we continue through these chapters, there's really nothing crazy for the most part that we come across in terms of reactions that you should start like making cool looking structures, just kind of putting things together. It pretty much stays exactly the same as it is, where you started. The only difference really is, as I mentioned, one spot that changes. So if I were to have this problem and I were asked to draw the product, I pretty much would copy what I have on the left-hand side. Obviously, I would not copy the stuff that I'm taking off. So pretty much you could just really no brain it there, no thinking involved, just copy what is there. And again, I'm going to copy 100% everything except for pretty much the 2 things that I highlighted, which obviously came off. Now, the result of those guys coming off, as we talked about in organic chemistry, pretty much you always sacrifice 2 hydrogens when you put on a bond. So in this case, we basically just sacrifice 2 hydrogens, and the bond always goes between the 2 places where you took the hydrogens from. So the 2 places that we took the hydrogen from was the oxygen and the carbon. So that is where we should make our double bond. And there you go. Kind of a curvy double bond there, but it kind of works, yeah. It doesn't matter, honestly. And truthfully, I'm probably more interested in the second thing anyways. But if you want to really complete where everything went, you should throw the H2 on the other side somewhere. But I'm probably more interested in sort of the structure here that you sort of ended up with. Yeah. But to answer your question, it doesn't matter. As long as it's technically on that side of the equation, it's good. It can come first or second. It doesn't matter. Other question? Yeah. It doesn't in terms of the carbon you're asking? Yeah, it does matter. The 2 hydrogens always in this situation, it's got to be one of the hydrogen has to be the one attached to the oxygen. And then in terms of the carbon, if that's your kind of your second question, is technically you take either one. So, you know, if I took the guy to the right, it's fine to just leave the guy on the bottom. You just draw the guy on the bottom and it's the same thing. I actually took the guy on the bottom so you can kind of clearly see the functional group that we end up with. But in terms of the carbon, you could take either one of these, just not both. You just gotta take one. So whichever one you want to take, you can take that one. That is always the deal in this, 100% of the time. Always the H off of the O and one of the H's off the carbon. And again, because we took an H off of the O and one off of the carbon, that is where we then insert our double bond for the loss of the hydrogen so that everybody still has the right amount of bonds and electrons. Although in organic, we don't draw the dots here, but there are dots, just like in Lewis structures, technically speaking, you know, there are those dots that are there. What we get here as a result of this oxidation reaction is another organic compound, which is known as an aldehyde. And the aldehyde's functional group is that last part there. It is this part right here. It is a carbon to a hydrogen with a double bonded oxygen. So that is the functional group of an aldehyde. And maybe wake up. So the functional group of an aldehyde is the carbon oxygen double bond with the hydrogen. So we make an aldehyde from the oxidation of a primary alcohol. Any questions on that? Now, if you have the secondary alcohol, like we talked about there at the end, and again, I'll just draw one of those guys here. Let's do. Can you silence that, please? Thank you. Okay, so if we look at this, which is a secondary alcohol, again, if it goes through our oxidation, once again, here we're looking at the loss of the hydrogen. And as we just talked about, we're going to take the hydrogen exactly from the same spot. So 100% of the time is going to be that hydrogen off of the oxygen. And in this case, there's only one option here for the hydrogen here on the carbon. It's got to be this guy right there. And that is, again, the H2 that's going to come off. Remember when we're talking about taking the hydrogen off the carbon, again, it has to be the carbon that's attached directly to the oxygen. That's where the hydrogen has to come off of in this particular case. Again, you got lots of hydrogens all over the place there, but there's got to be those two. That again is going to generate our H2. And once again here, if I were going to draw this, I pretty much would draw exactly what I got on the other side, except for our two hydrogens there in yellow. So the nice thing about a lot of these are you kind of have the answer almost in front of you. And if you're just not afraid to actually just copy what is there, you'll be in good shape. Again, you can see I pretty much didn't change anything there. I just took off the two hydrogens. And just like before, since we took a hydrogen off the oxygen, one off the carbon, that is where we should lay up our double bond in this particular case. This creates another organic compound, which is known as a ketone. And the functional group of a ketone is 3 carbons in a row with an oxygen carbon double bond happening in the center carbon of that. And although it is kind of heading downward here in this picture, here is our 3 carbons in a row, 1 carbon, 2 carbons, and 3 carbons in a row. And off of that center carbon, we have our oxygen double bond. So that is the ketone group that is there. Any questions on that there? And we finish up talking about the idea that a tertiary alcohol will not go through an oxidation reaction because it is missing a hydrogen there on its carbon. So I just dump this off here. So if we had our tertiary alcohol that looked something like this, if I just draw out all the hydrogens. The situation here is not too bad in terms of our tertiary alcohol, but we do run into a problem there at the end. We do have the blank screen. We do have a blank screen, a non-blank screen. I'm just gonna hit all the buttons and see what happens. So we obviously do have our hydrogen here that is necessary, but what we are lacking is the second hydrogen on that carbon. So because it does lack that second hydrogen, we really do not get any type of oxidation reaction occurring because no hydrogen there. We get no reaction. So a tertiary alcohol will not go through an oxidation because of the lack of that second hydrogen that is necessary for that. Any question on any of those reactions there? By the way, as we'll see when we talk a little bit more into aldehydes and ketones, the reverse reaction is again the reduction reaction that occurs in each of these cases. And the reverse reaction here is actually the definition of reduction, which is if we were going in the reverse direction, these guys would gain hydrogen going backwards. So if you add hydrogen to an aldehyde, you get back your alcohol, your primary alcohol. And if you add a hydrogen to a ketone, you get back your alcohol, secondary alcohol. Any questions on any of that stuff there? This slide. Now, in terms of the reaction that occurs with a primary alcohol, it actually can continue to go through a second oxidation step after the first one. And if you continue to sort of oxidize that primary alcohol through to one more step, you can actually create another organic compound. Good, whoever that was, yeah. So if we take our primary alcohol, which would have started from obviously what we had earlier there, which was this primary alcohol. And obviously went through an oxidation step. If you take that aldehyde now and actually oxidize it one more time, the definition that we get for the second oxidation is actually the gaining of oxygen. So the first oxidation is really the loss of hydrogen. The second one is the gaining of oxygen that occurs here. And there's a lot to it, but what eventually happens is there's an oxygen that gets inserted there along the way. Some other things are made and removed and moved around, which is outside the scope of our class. But the end result that does happen is simply you just have one oxygen that basically ends up right there at the end if you take the aldehyde and oxidize it one more time. Now, you may be saying, you know, how do I get there if I'm drawing it? The same rule applies. If you started with this and just understand that you just need to put an oxygen in there, you once again could copy exactly what is there. And simply at this second step, you just need to insert the oxygen. What this makes is another organic compound, which is known as a carboxylic acid. That's another organic sort of group. And the functional group is what I just boxed there. It is the carbon oxygen double bond with the OH. Sometimes in formula form, people just write COOH. So if you see COOH, it is what is basically in the box. Is sometimes how it's written. Like we might have talked about acetic acid, which is written like that. So it is actually a carboxylic acid, which is actually this guy right here is carboxylic acid. So that is actually the formula for it. And sometimes it's written COOH, and it is this part of the compound that is that COOH. So again, you could actually take your primary alcohol through two sort of consecutive oxidation steps. The first one is what we just talked about, the loss of the hydrogen, and you form the aldehyde, and then you could take the aldehyde through one more step, and it actually will just put in an oxygen in there. And by the way, the oxygen will always end up in this exact location when you go through this step right there with the H, because that's what makes it part of the functional group. So it always just end up right there. Any questions on that there? Okay. All right, so here's just some of the pictures. We kind of jumped ahead a little bit the other day, but again, here's our secondary alcohol. And once again, the double bond ends up right there in the center. And it is, as we talked about, H from the oxygen, H from the carbon, and again, just putting our double bond in place of that. Everything else, again, remains exactly the same on that oxidation step. And as we talked about as well, again, the lacking of the hydrogen prevents this guy from going through that oxidation. And again, that's our tertiary, the lack of the hydrogen on that carbon, preventing it from doing so. All right, so let's talk a little bit about some of the alcohols here. Methanol, also sometimes referred to as methyl alcohol. And that's sometimes a common name that people use for alcohols, you know, and it's because this is methanol. And they kind of name it like a group, right? That's like a methyl group, and that's an alcohol, so they call it methyl alcohol. Just like if you had our guy here, that is a ethyl group, right? So instead of ethanol, some people call this ethyl alcohol. I name it like by the group. So methanol here, again, being oxidized to what is known as methanol. Again, this is an aldehyde. And we see that group right there. And this is what is known as methanoic acid. Kind of a preview of these names, but you can see they all really go back to one carbon in each of them. They all go back to methane, basically. The alcohol becomes methanol. The aldehyde actually becomes methanal, Al at the end. And the carboxylic acid becomes oic acid, so methanoic acid. So again, all these groups, as I mentioned earlier, really do all come back to those alkane names with just a small little tweak in terms of what happens. There's ethanol, and again, our oxidation to our ethanol, which is our aldehyde. And from ethanol, you could oxidize it to carbon dioxide and water through a process there. By the way, again, the names in the parentheses here are more the common names that are sometimes used for these guys. Here are some of our phenols, and again, you can recognize the phenols by the benzene ring that is here. By the way, the benzene ring, as I might have drew last time, is also sometimes just drawn with a circle in the middle to indicate those three double bonds that we saw earlier. Sometimes you can just draw it like that. So here's again some different phenols coming through here. So the next organic group we're going to talk about here is thiols. Thiols are sulfur-containing groups. So the functional group for a thiol is SH. SH is similar to the hydroxide group, except that it has sulfur in there. It oftentimes has very strong odors, because if you ever smelled sulfur, you don't want to smell it again in a lot of cases, you know, so it does not smell so good. used to do experiments where they used a lot of sulfur, and it was not pleasant days in the lab in those experiments. Obviously found in bad things that we don't want to smell. Also, they put it into gas, right? So you know that the gas is actually leaking. Gas really doesn't have a smell, so they actually put some sulfur in there, so you can go, wow, that doesn't smell so good. Maybe I should look at that. Our skunk, I think that's what that picture is. I think. So let's talk about naming thiols, and let's not. So let's not name thiols, but in case you're curious on how to name it, you don't have to worry about naming thiols, but just for Jeopardy information, I suppose. Basically, we kind of just put thiol at the end, and you start with basically the carbon chain that's there. So for example, here, this is 2 carbons, which is basically ethane. And this is a thiol group. So ethane thiol is basically how you come about naming it. You also do need to, very much like an alcohol, sometimes give the location where it's at. So there's a couple of spots where you could have that guy located, either carbon number 1 or carbon number 2. So very much like before, we still have the 4 carbons, which is where the butane part comes from. This is a thiol, and kind of like how we named the alcohols, we give the location of where that's at. You will not be responsible for naming thiols, but you do need to know the functional group of it. And you do need to know a, yeah, here. So you don't have to worry about naming, but you do need to know the functional group, like I said, and you do also need to know a reaction that thiols undergo, which is kind of an important little reaction, which we'll talk about here in just a second, which is sort of a oxidation reduction reaction that basically occurs when 2 thiols sort of come together. Good. Yeah. What's that? Yeah, that's it. The functional group for the thiol, which is the SH. And we'll talk a little bit about the reaction here that occurs when 2 thiols get together. I think we might see it later on too, but let's just do it here since we're looking at it. Let's just say we had 2 thiols. I'm just gonna do this move. And we want to react them together. Just do this. And we'll just do a small one there. So if we basically put 2 thiols together, what will happen is we will basically lose H2, right, which is a definition of oxidation. So what happens when 2 thiols come together in an oxidation reaction is we basically lose 1 hydrogen from each of the thiols. That's why I kind of drew them back to back like that. So we're going to lose those 2. And it's sometimes helpful to draw them back to back because basically we take out the hydrogen. And then pretty much what we do at the end of it is after the H2 comes off, we essentially just squeeze them together. So you basically just start drawing on the left-hand side there. On the left-hand side, I have a CH3. I have a CH2 and I have an S, which is what's in my first one. I'm going to skip the 2 hydrogens that I took out and just continue on to the other side, which means I have another S and a CH3. So when 2 thiols come together in an oxidation reaction, we lose hydrogen, H2, 1 hydrogen from each side, and then basically you throw them together. Sulfur to sulfur is the important part of how they need to come together, because this makes what is referred to as sometimes referred to as a disulfide bond or bridge. And that is a bond that happens between 2 sulfurs, a couple of amino acids. Well, 1 amino acid can do it with itself, and that happens, and you make these disulfide bond bridges. So the connection, though, when you put 2 thiols together, is always this connection. It's got to always be that sulfur to sulfur connection is how they come together. Then obviously whatever's on the other side of sulfur just stays on the other side, nothing changes. So that's the oxidation that occurs when you put 2 thiols together, and you do need to know obviously that one. And we also need to know the reduction reaction, which is basically the opposite. So if I just take something like this. And I put it through a reduction reaction. The definition of reduction is it will gain H2 in this case. So it will gain H2. So sometimes it may say reduction, or it may just say H2 up on top of the arrow, or it may just say plus H2, something like that. But that's basically the reduction reaction that will happen. So since I missed a sulfur in my drawing there, let me fix that there. So we actually have the correct thing there. Sorry about that. It'll probably help if I have another sulfur there. There we go. I had 2 carbons after that, I think. Right. There we go. There we go. So because the connection when they do come together is always between the 2 sulfurs, this is basically the opposite reaction, which is going to break it back apart. So it's going to break back apart right there, right, between the 2 sulfurs. So when they come together and connect through the sulfurs. When you do the reduction reaction, you're basically just going to break them back apart through the sulfurs. And to draw what you end up with, I would again copy what is there. So I'm going to copy what's on the left. And since I'm running out of room, it's going to go above it. So on the left there, I have CH3, CH2, CH2, and S. That now is like 1 thiol, but it's missing one thing. It is missing a hydrogen, right? Which is good because we put in 2 hydrogens. So there's 1 hydrogen. Then I'm going to draw what's on the other side. And that guy also needs the 2nd hydrogen, right? So we just put a hydrogen in there to the sulfur. And then we pretty much just copy exactly what we got going on there. So this is the result of it. We'll go this way. When you break it back together with a reduction reaction. So 2 thiols oxidation, take out the H2, stick the 2 sulfur sides together, and you put it together, make that disulfide bond or bridge. And if you start with like a disulfide bond or bridge and you add hydrogen or go through a reduction reaction, you basically break it dead center there on the sulfur, separate out each side, and everybody gets a hydrogen, 1 on each side, and you'll have your product there. Any questions on those 2 reactions? So for thiols, like I said, you don't have to worry about naming them, but do need to know the functional group and these 2 reactions, how to properly obviously draw the products that you would get here. Any questions on any of that there? I hope you can start seeing on some of these reactions that it is not as complicated as people really like to make things. Yeah. So you want to keep it very, very simple when you're doing these things. And like I said, don't overlook the fact that you pretty much have the picture already drawn for you, the problem. So you just got to remember what part of it changes and just change that part and put it together correctly. And again, like I said, there's nothing that we come across in this class that does anything weird. Like there's none of these things will decide, hey, I'm just going to go into like a ring or something like that, which is a very popular thing people like to do. It's going to draw some cute structures and stuff like that. So keep it simple. Go based off of what's happening in the reactant, and you should get pretty close and hopefully the right sort of structure on the back end. All right. The next type of group we're going to talk about, which is an oxygen containing group, is an ether. The functional group for an ether is a carbon, oxygen, carbon. So that is a carbon, oxygen, carbon move there. And that is what you need in a row there with the oxygen, nothing else attached to the oxygen. So that carbon, oxygen, carbon run. If you see that somewhere, that is an ether. It is a bent structure because, again, although sometimes not drawn a lot in organic, there are the non-bonding electrons there, which gives it the 4 electron pairs and 2 bonds, which is just like water, bent or V-shaped. It gives it that overall geometry that occurs. It cannot hydrogen bond because it does not have hydrogen, right? To do so. So alcohols, by the way, going back to alcohols have very high boiling points. I think we might have talked about last time as well, because of the ability to hydrogen bond with itself. So if you remember, hydrogen bonding is one of the sort of strongest intermolecular forces you could have. So because alcohols have a OH group and it can hydrogen bond with itself, it has very high melting points and boiling points. So things that have weaker sort of intermolecular forces have much weaker boiling points and melting points. And those are like things like our alkanes, our alkenes, and our alkynes. They're all just carbons and hydrogens, which is non-polar. And those guys use dispersion forces as their main source of intermolecular forces, which means they typically have a much lower melting point and boiling points, which is why those guys go into the gas phase really easily, as I think we talked about when we talked about that chapter, because of that. You do need to know ethers, and we're going to go with the common naming of ethers. So this is really not the IUPAC way of naming. The common way to name ethers is simply, my recommendation is find the center oxygen in your 1 carbon oxygen carbon run. And pretty much you look to the left, you look to the right, and you see what groups are there. So if we do that, to the left is a methyl group, right? To the right is a methyl group. So that is 2 methyl groups in that compound. So that is dimethyl, and you just throw ether at the end of it. So that is dimethyl ether would be the name of this guy. You know, if you had again, this is an ether. We have a carbon, oxygen, carbon. And once again, here I'm going to look at the oxygen. And over here, I have a methyl group, right? 1 carbon group. Over here is a 2 carbon group. And that is a ethyl group. Much like everything else in organic, we would do alphabetical here. So we would go with ethyl, methyl, and just put ether at the end of it. So we will do the common name for ethers. And again, basically just locate that oxygen. Left and right should have a group, and you'll name those guys as groups. And then you would, excuse me, and then give the name. The IUPAC way of naming is you take the longest carbon chain. So we'll just do this one. And that's the base of your name. So that's ethane, right? And the group gets like oxy at the end of it. So that's what is known as methoxy ethane was the IUPAC way of naming that, which is why we're not going to do it. So we're going to do the common way of naming here, which is to the left and to the right is how you would name it. Just in case it pops up somewhere, you kind of put oxy on the group that's attached, and the other guy gets kind of the full name at the end of it. So again, here looking at naming ethers, sort of our common way. Here's our ether group, carbon, oxygen, carbon. Once again, put a little box there around the oxygen. To the left is a 1 carbon group, which is obviously a methyl group. To the right is a 1, 2, 3 carbon group, which is a propyl group. And again, like I said, alphabetical order here in terms of the groups. So methyl, propyl, ether would be the name here. Any questions on that there? Now let's say we had, why don't you draw ethyl, pentyl, ether. You could draw the condensed structure if you like. We'll approach this the same way as we talked about when you're given the name and just kind of working backwards. So in this case, we do have ether. So I would recommend in this case, instead of kind of doing the carbon skeleton, is to start with just the ether group, which again is basically, we'll go up here. So I would go with the carbon, oxygen, carbon as sort of my starting piece here, since I know I got to have that, right? And since this is really the common name of it, I know to the right and left of my oxygen there, I should have those groups. So that sort of takes care of the ether part. Pentyl would be how many carbons? It would be 5, but since I kind of started with it, I got to remember I already have a carbon, so I'm just going to write it to the right. It doesn't really matter. You can go left or right. It doesn't really matter. So I really have 1 carbon, so I'm just going to add 4 more to it to get me to 5 on that side, which would then give me my pentyl part. Then obviously my ethyl would go on the other side, right, of my oxygen. And again, I already kind of have 1 there from drawing the ether group. So I actually just need to add 1 more carbon there, and that would give me the 2 that I need. And just like everything else we do, everybody else is going to be hydrogens to get to 4. So this guy here would need 3. This guy would need 2, 2, 2, 2, H, and 2 and 3 at the end. So a little bit different, but kind of similar. Again, since it has that special sort of connection for the group, and it is kind of in the middle of everything, that's sort of a good place to start, especially since we'll use the common way of naming this, so you can kind of then put your groups on either side of the oxygen. Any questions on drawing that? So obviously for ethers, you need to know the common naming, obviously, and how to, obviously, if you're given the name, draw the structure, the functional group for it. Let's talk a little bit more about ethers, right? They put you to sleep, right? And all that good stuff. So over the years, they've sort of varied a little bit of the use of ethers. They've kind of swapped out a lot of the hydrogens that were there for things like fluorine, which makes it a little bit more tolerable for some people. But they still basically all have our basic ether group that is located there. And again, kind of swapping out some of those fluorines, reduce the volatility and also flammability, which is kind of good as well. You probably don't want that place exploding into flame, I'm imagining. All right, so let's draw some structures here. Let's do 3-pentanol, ethanol, diethyl ether. Let's do let's do 4-bromol, 2-pentanol. You can draw the condensed structures for this, is fine. Let's do ethyl propyl ether. And let us do 2-methyl cyclopentanol. All right, so structures on the right and structures on the left as well. Let's do both. Again, the OL here tells me it is an alcohol, so it obviously should have an OH group. The kind of pentane part tells me it should have the 5 carbons. So that is where I will start with, which is our 5 carbons. Uh, 3-pentanol tells us the OH group is at carbon number 3. And as we talked about, since you are drawing, you could number left to right or right to left. Again, I'm going to kind of go left to right here, which means for me, that would be my 3rd carbon where I'm going to put my OH. The rest here, obviously, are going just to fill in with the appropriate amount of hydrogen. So that guy needs 3. This one has 2 lines coming in, so it needs 2. The one with the OH group actually has 3 lines coming in, so it just needs 1 to get to 4. This guy's got 2 lines, needs 2 to get to 4, and the guy at the end needs 3 hydrogens there to get to 4. Any questions on that one there? Now, ethanol, OL again tells me it's an alcohol. Ethanol tells me it's ethane, which is 2 carbons. And that's pretty straightforward. So we're going to go 2. And really, this is one that doesn't have a number because, frankly, wherever you put the OH is the first carbon. So if you put it on the left, it's number 1. You put it on the right, it's number 1, which is why you don't really need a name because it's the same molecule. You just turn it around. So I'm just going to throw it over here on this carbon. And that means this carbon needs 3. And this guy would actually still need a couple of hydrogens there. And that would be ethanol. Again, if you throw on the first carbon, you're good as well, the OH group. And obviously it'd just be turned, basically, the molecule. Any question on any of those 2? Here we have diethyl ether, which is our common name. So the ether part, again, in this case, I would start with that part of it. And the ether functional group is the carbon, oxygen, carbon kind of move. And remember, basically, we're going to use that oxygen as our centerpiece. And we're going to go left and right and put the groups that are there. And in this case, it's diethyl, which basically means there's an ethyl group on each side. And ethyl is 2 carbons. So I also want to remember I already put a carbon on each side. So I don't want to put in there 2 because then you put a propyl group. So here I would just need to basically add 1 more carbon with the appropriate hydrogens and 1 more carbon here with the appropriate hydrogens. And obviously these would all be the condensed formulas for all these guys here. Any questions on any of those there? Okay, so go with the ones I made up, which apparently pentanol was in my head a lot here because I probably saw it there. So maybe I'm just going to steal what I got drawn here. Let's see here. I don't know. Maybe I'll do that. We'll just draw it again. So same idea. We got pentanol, which again, we're going to lay up our 5 carbons. In this case, though, it is 2 pentanol, which means our OH group is going to be on carbon number 2. So for me, I'm going to go left to right, which means that is going to be carbon number 2. So that takes care of that. Because I chose that as carbon number 2, obviously that's carbon number 1, number 2, number 3, number 4 would be to the right here, which should have a bromine attached. And again, at this point, there is nothing left but hydrogens to finish it out. And that would be 3 there, 1 there, 2 there, 1 there, and 3 there. Again, remember the hydrogens are put on to get carbon to 4 bonds. So you just want to count how many bonds are going to that carbon and then add the appropriate amount of hydrogens to get you to 4. Any questions on that one there? All right, then I have ethyl propyl ether on this guy. So we'll squeeze them in right here. Once again, I'm going to start with the ether group, which is our carbon, oxygen, carbon. So that takes care of that. In this case, I have a propyl on one side, which is a 3 carbon group. And again, it doesn't matter if you drew it to the left or to the right. I'm just going to draw it to the right here. So that should be 3 total carbons. So in my case, I just need to add 2 more to get me to 3. And we have an ethyl group on the left. Again, I already have a carbon there. So just going to do 1 more. And now we're going to put obviously our appropriate amount of hydrogens in, which would be 3 for that guy, 2 for that guy. Oxygen doesn't get any hydrogens, obviously, in this case. The 2 there, 2 there, and 3 there. Questions on that one there? All right, last one. Hey, pentanol, what do you know? All right, so that is cyclopentanol. At least I changed it up a little bit there. So cyclopentanol, right, is our ring structure, right? It's basically based off of cyclopentane. So that's a good place to start with. I'm going to just kind of draw that. And usually line structures, a lot of times what we kind of use for those kind of cycloalkane-ish. The OL means there's an alcohol, and frankly, you could put it at any spot along that ring you like. I'm just going to go straight up with it here at the OH. So that really is the cyclopentanol part of the production. We then have 2-methyl, which means, frankly, you can go left or right. I'm just going to go clockwise and put it over here. And we would have a methyl group hanging out. Again, this is assumed, obviously, because it's the OH to be carbon number 1. So that is obviously how we get to carbon number 2, kind of going to the right of it. If you drew it to the left, 1 carbon over, it's fine. It's all right as well. Yeah. Any question on drawing any of those structures? All right, last one here is a reaction. So you should hopefully recognize these guys as thiols. And when you have 2 thiols that are separated from each other, pretty much the only reaction we talked about is we're going to put it together. So sometimes visually to help you, since they are not lined up with sulfur to sulfur, you may just want to turn one around. So you may just want to draw right above it, kind of lining up the sulfur and basically just writing the rest of it. And I'm just recopying the guy below it and basically just kind of turning it around. So it's kind of in the right orientation for you. It makes it a little bit easier. So I'm just going to kind of put a line through that guy because I just kind of turned it. What we know should happen, right, is we should take out an H and an H, right? So that's going to come out. And again, sort of the benefit maybe of turning that guy is now, frankly, all I have to do is start on the left-hand side and go to the right-hand side and just draw what's left. So doing that, started on the left-hand side, I have a CH3, a CH2, and an S. That pretty much took care of all that. Remember, the connection is always the sulfur to the sulfur, which brings me to the other guy. And now I'm just going to continue copying what's left there on the other side. And we do a little bit of that, a little bit of that, and a little bit of that. There we go. and we make our disulfide bond bridge. That's the scientific thing, that a little bit of that as well. Any questions on any of those things there? Yes. Obviously, if we were to do the reduction and we started with the guy on the right, you just split it right there at the sulfurs, separate them out, add a hydrogen, and that would be basically the reverse reaction, which would basically be going in that direction. All right, good, yes. All right, so some properties of alcohols. As I mentioned before, alcohols really do participate in hydrogen bonding because of that OH group. Obviously, it's a major part of hand sanitizers, which we all became very familiar with recently. Make sure you have the right amount of it in there as well. We talked about the classifications earlier in relationship to talk about some of those reactions. But once again, you know, looking at the OH group, the carbon that has it attached, we have one carbon, which is our primary, secondary, and our tertiary alcohol. So why don't you classify these guys, and while you're at it, why don't you name them as well? Classification first. So in classifying, definitely want to look at the carbon that is attached to the OH, and we want to look and see how many carbons are directly attached to it. So there's one and there is two, which means this would be a secondary alcohol. Looking at the carbon on the second one that is directly attached to the OH, we see that attached to that carbon is just one carbon attached to it. So that would be a primary alcohol. And lastly, looking at the carbon here, which is directly attached to the O, we see 1, 2, and 3 carbons directly attached to it, which would mean it is a tertiary carbon or tertiary alcohol. Any questions first off on the classification part? Now that we have the classification part down, we're just going to name it. So longest carbon chain that does have the OH attached to it would obviously be straight across there. That is 4, which is based off of butane with the OH group. It becomes butanol. Do I need to give the location of the OH group? I do need to give it, which is 2 in this case. Again, anything 3 and above, you kind of got to give that location. Question on that name there. Longest carbon chain here on the second one is 3, which is based off of propane. So it becomes propanol. Do I need to give the location of the OH group? You do in this case, and it is at carbon number 1 here. So this would be 1 propanol, because you could have put it right there at carbon number 2, and it would have been 2 propanol or isopropyl alcohol. So in this case, 3 or more, you do need to give that location. And lastly here, longest carbon chain actually is the straightest, I think. And that is 5, which is based off of pentane. That then becomes pentanol. OH group does need to be numbered, and actually it doesn't matter which way you go, it's going to be 3. And by the way, it doesn't matter either for the group that's also hanging out there at carbon number 3. And that means it would technically be 3-methyl 3-pentanol. Yeah. Any questions on on that there? Yeah. Are we talking about the last one? Yes. Which the one I circled? It wouldn't, because the other thing attached, if you're talking about this guy, that's actually the alcohol group or the OH group. Yeah, so that's incorporated into here. If it, yeah, so if it was like another methyl group there and like the OH was over here or something, then you would have that. But in that case, it's actually the functional group, that OH, which gets incorporated into the main part of the name. So although it is sort of a group, it's part of the main group. Other questions? All right, we will lay it up there for the week